I'm Cara Pizzelli. I'm a process development scientist, and I'm here today to show you how we're going to set up and run a PMax experiment. So you would consider running a PMax experiment if you're looking to compare different depth filters or run an experiment to look at what size you would need for a depth filter for, say, a mammalian cell culture harvest, or potentially a step after protein A where you're looking to remove precipitates or a haze. You may run a PMax experiment for an E. coli or a yeast lysate. A PMax experiment is a constant flow test where you're running at continuous flow rate, and you're going to collect information to see how the depth filter behaves as it builds up pressure. So you want to run it to a maximum pressure of, say, 20 psi, and you would be collecting data that I'll discuss later in the video. So the first part of the video, I'd like to share with you the equipment we have here set up. We'll start from left to right. We'll start with the beaker that we're using here. It's filled with water. If you choose to prime with buffer, you can do that. Once we're done with the water for flushing, we would dump that out and fill it with product. Now we would be using silicone tubing, and sometimes I like to put a pipette, like a 1 mil or a 2 mil pipette in there, to keep it from kind of bouncing out as the tubing's naturally vibrating as you're running the pump. We have a peristaltic pump here. Basically any positive displacement pump will do. We have the MilliStack Plus depth filter here. This depth filter is our small scale, and it's 23 square centimeters. I'd just like to point out that as you're running your experiments, I would take note of what the area is in case you are testing a different filter that might have an area of 25 square centimeters or 26 square centimeters. The slight difference there will actually matter when you're doing the data analysis at the end. So then we also have a pressure gauge here, which is connecting the inlet tubing to the inlet of the filter. So you see you would have your pressure gauge. This is connected to the filter using a Lure T. Also on the front side of the filter is the vent. So here we have a 3-way Lure valve. You can use a 2-way Lure valve. You could actually just connect the tubing directly to the filter and use some type of clamp. On the back side, we have the same 3-way valve. Again, could be a 2-way valve, or you could use a clamp on the silicone tubing. If you had PharmEd tubing instead, any type of flexible tubing would work. You will need to know what the size is so you can accurately set the flow rate on the pump. In this setup here, you may notice that the tubing size looks a little different. We have size 16 on the inlet and the vent, size 14 on the outlet. There really is no strict reason why you need to have all 16 or all 14, but whatever you have available in your lab would be fine for this scale experiment. This was set up for our demonstration. And then you also have another beaker that's going to collect the filtrate, and this is right now on a balance so that we can record our volume. You can use a graduated cylinder or any other type of weight or volume measurement. With that said, oftentimes we assume that the fluid we're testing is close to water, so the density would be around 1. But if you know that your material would have a different density, that would be good to record, and again, that would be accounted for in the data analysis section. So when we start, we're going to start with water flushing. So you can find this information in our user guide, which would be on our website, or you could contact our tech service or your account manager. And the specifications for flushing are 600 LMH. LMH is a flux term, and it's liters per meter squared per hour. So when you do the calculation to account for 23 square centimeters, your flow rate is approximately 23 mils per minute. And we're going to flush until we reach 200 milliliters in the bucket, and that's going to be equal to 100 liters per meter squared for a volume for loading. So when we start the flushing, we're going to close the filtrate, we're going to open the vent, and we're going to turn the pump on. So it may take a few minutes for you to fill the line with water, fill the filter with water, and then you'll see that you're displacing all the air that's on the upstream side being the side where unfiltered material will go, and then you'll see that the air is coming out the vent line and then it's displaced with water. Once you've vented your filter, then you would close the vent and open the filtrate so that now your material is being pushed through the depth media and will start collecting in the bucket. So again, for the sake of the video, we will not fill this all the way up to 230 mils because we are going to use water in place of our product. But once you would reach the 230 milliliter mark, you would stop the pump, you would discard your material, you would dump your water here, and then you would fill this with product. Now, when we run with product, I would just say that the depth filters do remove particles and debris based on size, but there's also an absorptive property to the depth media that will remove smaller colloidal matter and other insoluble impurities. So what we like to do is reduce the flow rate to about 4 to 8 mils a minute, which is equivalent to 100 to 200 LMH. And this will allow us to have a little bit of residence time in the depth filter so that you can take advantage of the absorptive qualities. So I'm going to reduce this down to about 8, so that would be 200 LMH. I would say that's a good place to start. Gets the experiment done a little bit quicker. And if you feel that there could be some optimization, you could look at doing lower flow rates at a later time. And while I'm doing this, I'll also like to just point out that if you do need to account for the volume that's being held up by the tubing and the filter, you want to make sure that you measure the hold-up volume at the start when you're flushing. So what you would do is at this point, I guess before you discard the water that's in there and the water that's in here, you would do a mass balance. You would basically add the volume that was put into the system and all the volume that came out. And you would subtract what you started with to find out what's held up inside the filter and the tubing. Okay, so when you're getting ready to start your experiment, you want to make sure that you have a stopwatch, and you want to have basically a data sheet where you can record with time. You can record the volume that's coming out the filtrate. You can record the pressure, because as you are collecting particles and debris, you're basically blocking off the filter, so you should be building up pressure. And you also periodically want to take a turbidity measurement. And this turbidity is recorded in NTU, which is nephelometric turbidity units. And this actually measures basically the cloudiness of the material coming out. So it gives us a sense of basically how clean the filtrate is. And again, the filtrate is the stuff that's coming out the downstream side of the filter. And you may want to take that measurement, say, every 10 to 15 minutes, where for the time, volume, and pressure, you probably want to record every couple of minutes. It's up to you. You can take a look. As the pressure is building up, you may want to take some more measurements more frequently. So now I will start the timer and start the pump. So when you're running your experiment, again, I mentioned early on that you would run to a maximum pressure of 20 psi. So we have some specifications on our filters. You can have a maximum upstream pressure of 50 psi. You can have a maximum differential pressure of 30 psi. Differential pressure being the difference in pressure from upstream to downstream. And downstream is open to atmosphere, so that would be 0. So we suggest 20 because you cannot model the PMax performance. So you have to physically see and observe the behavior. And by behavior, it's basically what's happening with the filtrate, how turbid is it, how quickly is it building up pressure, and how much volume can you get through by the time you reach 20 psi. Okay. So as you're recording your data, the turbidity vial will require about 13 to 14 milliliters of product. So depending on your flow rate, it may take a few seconds to fill, a few minutes to fill. So you would just sort of hold it in the vial till you get just above the point on the vial. Sometimes I might put an extra clamp here, and you can sort of have it clamped over the bucket. I like to do it over the bucket in case you walk away or you start doing another measurement. That way you're not spilling onto your lab bench. So sometimes these experiments can take quite a while because you have to run it basically to an endpoint. We don't know how long that's going to take. It could take anywhere from 2 hours to 4 hours to run your experiment. So then once you have your vial filled, you would want to wipe it off with Kim wipe. Turn on your meter and take a reading, and then just record that, if you can, with a pressure and a volume. So yeah, another thing to look at when you're sort of collecting the data is that when you start, you're going to expect that over time the volume is increasing, the pressure is increasing because we're just continuing to remove particles. The turbidity hopefully will stay relatively low if you've selected the right filter. So sometimes you may realize that something is not quite right there. And one of two things usually happens if it's not going to follow that increase with pressure, increase with volume, is that the pressure sort of levels off at a certain point. But what you notice when the pressure is leveling off is that the turbidity is increasing. So when that happens, it's actually sometimes referred to as a Tmax, so like a maximum turbidity, or you've reached a point where, depending on the kind of particles and the size particles and the pressure, you're having what we call breakthrough. So the particles, instead of being captured by the depth media, are now breaking through and causing cloudiness on the downstream. What that says to us is if this is the right filter for you, you need to size it before that breakthrough. So whatever volume to area ratio you were at that point, that would be what you use to translate to the large scale. Another thing you might see is that the pressure may go all the way up to 20, and then you see it back off to like 18 or 17, and that's a little bit confusing. What sometimes happens, depending on the condition of your pump or how many times you've used the tubing, you may be seeing pump slippage, where it's just kind of skipping. And there's this pressure buildup, but then as there's a release of pressure between the rollers of the pump heads, the fluid just shifts back a little bit. And so it basically reduces the pressure when it does that. When we do the calculations for sizing, we normalize for all of these changes. So we normalize for area, in case you were using a filter with different area, and we normalize the volume for flow rate as well. So we can calculate the flow rate from the volume and time data that you're collecting. So now that you've collected all of your data, we'll just do a quick recap of the PMax method. This is a test that's run at a constant flow rate. You're running your process solution through the pump, through your filter, and the data shows that you're measuring an increase in pressure and a decrease potentially in filtrate quality as a function of throughput. The endpoint of your test is typically determined by a maximum pressure limit, which would be PMax, or a desired filtrate quality that you would measure with turbidity, which is Tmax. Once you have your table of data, which would be time, volume, and turbidity, you're going to use your time and volume data. You're going to plot the resistance curve. So you're going to have resistance on the y-axis and a loading or capacity number on the x-axis. Resistance is in terms of pressure over flux, which is liters per meter squared per hour. And the loading or capacity on the x-axis is liters per meter squared. So once you've plotted your resistance and your loading, and then you've used Excel to lay over that a second or third order polynomial equation, this part of the calculation is a bit iterative. Because you're using depth filtration, as I mentioned before, you cannot model this. If you were running at the exact operation as your large scale, same flow rate, same process time, you could just pick your maximum pressure as, say, 10 psi, and you could look to see how much volume you had processed per small unit area. But since that's not always the case, you usually end up running longer to reach your maximum pressure or your turbidity maximum. You need to run through a bit of an iterative method here to find the minimum area required. So you would have a known batch volume and a known batch time. You would select an area, which we will call a guess. A good first guess would be starting with your batch volume divided by your final test loading. You would select a pressure limit for a process endpoint. So typically if you have 2 or 3 processes in a train, 2 or 3 filters in your process train, and your maximum
pressure for that part of the operation was, say, 20 to 30 psi, it would be a good starting point to just divide it by the number of filters that you have in your train. So say you have 30 psi and you have 3 filters in your train, I would say start with 10 psi. So with that information, you're going to calculate a flux, which we'll call J average. This would be your known batch volume divided by your A guess and your batch time. You can also calculate the associated capacity or loading, which would be on the x-axis. This would be batch volume over the area. And then you're going to calculate resistance using your 10 psi or your pressure limit over your average flux that you just calculated. Then you're going to look at your best fit equation. So say it's a third order polynomial equation. This would be y equals ax cubed plus bx squared plus cx plus d. And your x is now going to be your capacity or loading that you just calculated in the second bullet. You're going to run through that calculation to calculate out y, which is going to be your resistance. And you're going to have 2 resistance numbers. You're going to have the R calculated from the third bullet, and then you're going to have the R actual from the polynomial equation. So if your R calculated is equal to your R actual, then you have made the correct guess for area. If your R calculated is less than your R actual, then you need to increase your area for A guess and start the calculations over again. And then if the vice versa was the case, so that R calculated was greater than the R actual, you would decrease your A guess value. And then you just continue to reiterate until your R calculated is equal to or as close as you can get it to your R actual. And this area that you've been calling A guess is now known as your A min, which is the minimum area required to process your batch volume within your batch time. So then what do you do with A min? Now you need to size for your large scale installation. We typically include a safety factor. For clarification, is between 50 to 60%. So what you would do is you would take the A min number, you would multiply that by 1.6, and we could call this A recommend. And then you would use, you could call customer service or a process development scientist, your account manager, a catalog, or a website for Millipore, EMD Millipore. And you can find the device part number for the selected depth filter area with an area that would be greater than or equal to A recommend. And this area could become your A install. And then if the A recommend is greater than the A install, you may want to recalculate what the actual installation safety factor would be by dividing the A install by your A min, and that would give you the actual safety factor at the large scale. And those are the calculations that would use to go along with your PMax testing so that you can size depth filters for large scale applications. Thank you.